Let's talk about Hamilton circuits some more. Remember, Hamilton circuit is one which uses every vertex once. So a Hamilton circuit uses each vertex once, exactly one time, and it doesn't care anything about the edges. So you can miss some edges if you want to. All that matters is you hit every vertex one time. For example, if I have this graph right here, this one does have a Hamilton circuit. For example, I could start here and just go around the outside, right? You might say, oh, you didn't go through the middle edge. It doesn't matter. You just have to hit every vertex, and this one does. There are 4 vertices, and my circuit there does get every vertex. One thing you'll notice, actually drawing, once you can locate them, drawing the picture of a Hamilton circuit is actually easier than with Euler circuits. Here is a more complicated example. Let's say we had, well, we saw this one last time at the end. This one does have a Hamilton circuit. The way to do it is, if we want to start here, for example, sorry, I didn't finish drawing the picture. This one actually does not have a Hamilton circuit. This one does, if you add one little diagonal like that. The way to do it is sort of go around this way, but then here you cut in, hit the one in the middle, and then come back out and go back to where you started. That hits every vertex. Because of the fact that a Hamilton circuit never revisits a vertex, actually it's much easier to draw them in an unambiguous way. In fact, this path, which goes around the edge and then goes in here and then comes back out, we can just draw that by sort of scribbling in edges, right? This is very easy to do if you don't have different colors. All right. And when you look at that, it's obvious which way to go. Unlike in an Euler circuit has to revisit vertices very often, and if you try to draw an Euler circuit in this way, it just looks totally confusing. But for a Hamilton circuit, it's totally fine. I draw this, you know what I'm talking about. The only thing you can't tell with the scribbles is which direction around it's going. Is it going that way, or is it going around that way? And typically, it doesn't even matter. That is a Hamilton circuit, whether it's clockwise or counterclockwise. It don't matter. All right. So we are typically going to draw Hamilton circuits in this way, with sort of the scribbly lines, the squiggly lines, just because it's easy enough to do that, and it still looks fine. Everybody can tell exactly what I mean when I draw it in that way. All right. So we're going to talk first about how could you find Hamilton circuits. If I drew a graph for you, how can you find a Hamilton circuit? Now, like I said in the last time, there is a very nice theorem and algorithm for Euler circuits. The theorem is, if all the degrees are even, then there is an Euler circuit, and if not, then there is not. So it's easy to tell if there is or is not an Euler circuit. And then there is Fleury's algorithm, which allows you to find the Euler circuit if you know it exists. There are no such techniques for Hamilton circuits. So there is no easy theorem that lets you know if that exists or not, and also no easy algorithm which lets you find a Hamilton circuit. So I'm just going to say there are no easy tricks to identify if/where Hamilton circuits exist in the graph. No one knows a simple condition that you can just look at the graph and immediately determine if there are Hamilton circuits or not. You could try to figure one out. There is no such known procedure. So, no easy tricks to identify if or where Hamilton circuits exist in the graph. All right? That means that what we're going to be talking about are kind of hints or little techniques which will sometimes work and sometimes don't work. Because that's as good as it gets. There is no sort of silver bullet that's going to let you do any example and find the Hamilton circuits. These simple tricks are very simple, based on very obvious observations that you can make about a Hamilton circuit. But they turn out they're kind of simple, but it kind of goes a long way. So I want to make 2 simple observations about the Hamilton circuit right here. You can see it right there. I gotta erase this. I hope keep this picture. So things to notice about the Hamilton circuit. Like those scribbly lines that I drew there, some properties of that circuit that I would like to call your attention to. And these are obvious once they're brought to your attention. It's not obvious why these are important, but you'll see in a moment. Each vertex meets two scribbled edges. Right? That's because this thing is supposed to be a circuit, and it has to meet every vertex. So it needs to arrive at every vertex once and then leave every vertex once. And that's it. It never revisits the vertex. So every vertex meets two of the scribbled edges. One, which is the one that the circuit arrives on, and then one, which is the one the circuit leaves on. No more than two, because the vertex is not revisited, and certainly no less than two, because the vertex is because every vertex must be part of the Hamilton circuit. All right, so this is one fact. Each vertex meets two scribbled edges. And the other simple fact from which all of our little tricks are going to be derived is that there are no smaller circuits among the scribbled edges. All right, that is because this is supposed to make one circuit which only hits every vertex once. There can't be another circuit like inside of it. What I mean is this is just supposed to be like one big circuit, right? It doesn't do something like that. This is what I mean by a smaller circuit, right? This big circuit has this other smaller circuit. Why doesn't it do that? Because this requires it to revisit that vertex, and a Hamilton circuit never revisits a vertex. So that means there are no smaller circuits among the scribbled edges in a Hamilton circuit. All right, these two facts are very simple observations, but actually very powerful and can allow you to either find a Hamilton circuit in a graph or show that no Hamilton circuit exists. Like I said, these don't always work, because there is no simple method which always works, not known to mankind, but they work a lot of the time. Let me just say a little bit more specifically about that first one there. The first one said that every vertex meets two scribbled edges. Two very specific things we can say about that. Let me just write the basic fact first. Each vertex meets two scribbled edges. What that means is, so, first of all, if some vertex has degree 2 in the graph, if the vertex only has two edges that hit it in the graph, then those two edges must be part of the Hamilton circuit. If a vertex has degree 2, then its two edges must be part of the Hamilton circuit. For example, in this example that I said a moment ago, right, this thing, where's the Hamilton circuit? If you're trying to find the Hamilton circuit and you, for whatever reason, didn't think to do that, I already showed you the example, but what if you didn't know the answer and you were trying to figure it out? One thing you can say is, if a vertex has degree 2, its two edges must be part of the same Hamilton circuit. Not same, of the Hamilton circuit. I can actually see there are some vertices of degree 2 here. This one has degree 2. This one also has degree 2. This one also has degree 2. All right? Once you know that, that means that these two edges must be part of the circuit. So wherever the Hamilton circuit is, even you don't even know where the whole thing is, but you can say it must go through here. It also must go through here. And it also must go through here. So already you've almost drawn the whole thing just because of this basic fact, right? If a vertex has degree 2, then its two edges must be part of the Hamilton circuit. Now, what is it going to do here is not as clear, but at least you have helped yourself out a great deal towards finding a Hamilton circuit, all right? So this can help you to draw a Hamilton circuit. Another thing we can say, very straightforward, if a vertex has degree 1, then this isn't even possible, right? In a Hamilton circuit, every vertex needs to meet 2 edges in the Hamilton circuit, right? That's what it says. Each vertex meets 2 scribbled edges. So if a vertex has degree 1, then that means there is no Hamilton circuit. Because if there were a Hamilton circuit, it had to meet this vertex with 2 edges, and it can't if the vertex has degree 1. So if a vertex has degree 1, then there is no Hamilton circuit. So an example of that where you could just immediately say there is no Hamilton circuit would be something like, well, sorry, got to erase. A graph which has a vertex of degree 1 would look something like this. All right. You would say immediately, this guy has degree 1, so no Hamilton circuit here. If you ever see a graph with any degree 1 vertices, it cannot have a Hamilton circuit. All right. We're going to combine these 2 tricks. Really, this second one is not usually going to be applicable just because it's so simple. If I were going to ask you a question on a test or something, I probably wouldn't put a degree 1 just because this can immediately dismiss such an example. But this first one is quite useful, especially in conjunction with the other rule that I said, which is the Hamilton circuit has no smaller cycles. Let's try some more complicated examples here. So the 2 big facts that you should keep in mind is that the Hamilton uses 2 edges at every vertex. Exactly 2. No more, no less. And that's the first fact. And the second fact is no smaller circuits. All right, I don't need that much space. No smaller circuits. And you'll see how that second one is actually quite useful also. All right, let's do an example. Your job here is either find a Hamilton circuit or demonstrate that none can exist. Now, this one also is fairly easy to do, even if you don't know any of these tricks. But I want to try and think it through in terms of the tricks here. So that in the future, if you encounter one that you can't do sort of in your head, then you would be guided by these 2 principles. Okay, this one, can you find a Hamilton circuit? It's got to use every vertex. Now, can I just say, this one is not hard to do, just sort of by common sense. How could you visit all of these vertices in a cycle? Well, actually, you can do what my hand just did. You can just go around the outside edge. There you go. You don't use those edges, but it doesn't matter. Hamilton circuit doesn't have to use all the edges. But I want to see how could we arrive at that answer without using any kind of common sense, only using these 2 rules. No appeal to just sort of think about it and trial and error. I'm not into trial and error unless I have to be. But I got actual ideas here. The first thing I realize is we have some degree 2 vertices. Do you see where there are degree 2 vertices? I see 2 of them. I see one right here. This is a degree 2. And I see one right here. That's a degree 2. So that means right away we can say the Hamilton circuit must go through there. And it also must go through there. All right? I am on the road to constructing the Hamilton circuit. Okay? Now what? If you should begin by marking off any degree 2 vertices you see. What can we do now? Well, at this point, we can use this second fact. There are no smaller circuits to eliminate some of these edges, right? Like some of these edges are going to get scribbled in. Some are, I suppose, not going to be used. I can say that these 2 vertical ones are not going to be used. So I'm going to just put like an X through them. Those edges cannot be part of the Hamilton circuit. Why is that? So I'm going to do a little narration here. Why can't these be part of the Hamilton circuit? It's because if it were scribbled in, that would make a smaller circuit, and that's not allowed by the second observation there. So these would make a smaller circuit. So we can't use them. That's why I X'd them out. All right. Okay, we can't use them. But now, this is like a sort of falling dominoes. Every time you kind of make one little adjustment, you will realize you can make new deductions. It's like a cute little puzzle that way. Check it out. Look at this vertex here. Now, we know the Hamilton circuit must meet every vertex along two edges. It already meets here. This edge is not used. That means we must use this edge because we only have one more choice for what edge meets this vertex. So this must be used. So I'm going to try to, when you do this on your homework or on a test or something, you got to give me some kind of narration about how you figured this out from step to step. So we began by drawing in edges on the degree 2s. Then we ruled out these two because they make smaller circuits. Then I'm going to say this one how about this? This vertex here now has only one choice for its two edges, right? Every vertex has to get two scribbled edges. And in this case, we had eliminated this one from consideration, and there were only two possible edges left, so I had to take this one because at this vertex, there was only one choice remaining for its two edges. And by the same reasoning, up here, this one also has only one choice remaining. We eliminated this one. I've got one scribbled. This one must be scribbled because every vertex needs two. So I'm just going to say also here. All right. Also at this vertex. And there we go. We have created the Hamilton circuit. It is what I said before. You just go around the outside. But I wanted to show how you could deduce that, not just by kind of guess and check, but by actually applying these two basic principles. Let's try some more examples. How's about, I'm going to leave that little box up there. How about this same old one that I've mentioned a couple times before? I just want to see if these two principles are actually enough to find the Hamilton circuit in this one. Like I said before, you begin with the degree 2s, and you can scribble all these ones sort of in the corners here. All right, there are no more degree 2s, so we can't do any more than that. Can we say anything else now? So first, I'm going to try and do a little narration here. First, we scribble degree 2 vertices. You should always begin like that. That's where you get something started. All right. Now, actually, we can X out some of these edges. For example, this vertex right here already has two edges chosen on the Hamilton circuit. That means there can't be any more. So this edge cannot be used by the Hamilton circuit. It's because every vertex needs to have exactly two squiggly edges. That one is not allowed. And similarly, this one is not allowed for exactly the same reason. So I'm going to say these vertices have two already, so we don't use the other. All right, I X'd out that edge, so I'm talking about this vertex and this vertex here. Okay, those two edges are not allowed. Actually, at this point, I don't think you can proceed by strict reasoning here. It seems like it is possible. Maybe you could scribble this top edge, or maybe you could scribble this edge going down. So I'm just going to say now we have options, it seems. And I'm just going to say I'll try this scribbly one going across the top. All right? So that may be part of your narration. If you feel like at some point you're just going to have to guess one edge, I'll try to go that way. But now actually everything else will fall into place. So the fact that I chose this one means I can X out this one, again for the same reason as before. So now this vertex has two, so we X the other edge. All right, I'm talking about this vertex right there. Okay. Now that I've X'd this out, this vertex now only has two legal edges that are still in play, right? All three of the others have been X'd out, and so I can scribble those in. And now I'm done. I have the full Euler circuit. And now this vertex has only 2 remaining. So use them. Use them. Right here, I'm talking about that vertex in the middle. All right, this is my little play-by-play narration. You got to give me that on the test or something, or on your homework, just because if you just show me the answer, your final answer, I know you can probably do this in your head without writing this down for yourself. You're writing it down for me, not for yourself. Do something for me every once in a while. Don't just think about yourself all the time. All right, I hope that's clear. Let's try some more examples. What about a similar thing, but with the diagonal going in a slightly different way? How about this? Similar thing, but let's say the diagonal goes that way. Looks like maybe this is going to be the same. It's not going to be the same. You should begin as usual by checking off or indicating the degree 2 vertices, right? And they are the ones in the corners. And actually, all 4 corners now are degree 2 vertices, right? So we are going to scribble all the way around here. Now what? Well, actually, the thing is sort of screwed right from the get-go. You can see, actually, we have made a smaller circuit. This already makes a circuit, but I haven't used this vertex. This is, it says no smaller circuits are allowed in a Hamilton circuit. So I'm going to say this made a smaller circuit. By smaller, I mean using fewer vertices. There are 9 total vertices here. I just made a circuit using 8, and that circuit was forced by the degree 2 vertices. So this made a smaller circuit. That's not allowed, and so no Hamilton circuit exists. Because just by handling the degree 2 vertices, it forced us into a situation where we made a smaller circuit. We were forced. It's not because I made a bad decision. It's because it was forced by the graph. That means that Hamilton circuit is impossible in that graph. All right. So this is, these 2 basic principles can allow you sometimes to find a Hamilton circuit. They can also allow you sometimes to show that no Hamilton circuit exists. Let's try some more. How about this one? Here's another one where no Hamilton circuit exists. All right, this is my graph. Do the same thing. So typical homework question or test question concerning this would just be like, does a Hamilton circuit exist or not? If it does, then show me what it is by scribbling. If it doesn't, then explain to me why it doesn't. You should begin by scribbling the degree 2 vertices. These 3 are degree 2 vertices, so I'm going to scribble here, scribble here, scribble here. All right. So I'm going to check the degree 2s. Then what? Actually, you can see we got a problem here. Can you see what the problem is? This one has no Hamilton circuit because I have already violated one of these conditions. I didn't make a smaller circuit, but I now have 3 edges of the circuit meeting at this point, and that's not allowed. So I checked the degree 2 vertices. This forces 3 scribbled edges here at this vertex, right? That is not allowed. Again, it's not because I made a bad choice. It's because it was forced on me by these degree 2 vertices. And so that means there is no Hamilton circuit in this graph. All right. There you go. Do you recall at the very end of last time, I had this example. And I tried to give you some kind of vague reasoning why there's no Hamilton circuit in this graph, but I said this is actually kind of hard to explain. Using these methods that I've been talking about, it's not hard to explain at all. When you mark off the degree 2 vertices, this is actually very much like the example that we just did 2 times ago. It had an extra diagonal, that one, but it doesn't matter. Here I marked off all the degree 2 vertices. But I already made a circuit and I missed this vertex, so this one has no Hamilton circuit. All right. I got some for you all to try. I got 3. erase this. I got 3 examples. See if you can, for each one, say where is a Hamilton circuit, find one, or explain to me why no Hamilton circuit exists. How about this is a pentagon inside a pentagon, because that's the kind of lifestyle I live. So it's a pentagon inside a pentagon with some extra vertices marked off like so. All right, see if you can decide, does it have a Hamilton circuit or not? I got another example. These are three separate examples. I'm just going to draw them all at the same time. All right, all these intersections are vertices plus those extra dots that I drew. And finally, this is kind of a big one. There, this is a big one. For each one, see if you can tell me, is there a Hamilton circuit or not? If so, scribble it in. If not, explain to me why not. See what you think. All right, did you try them out? Let's just go through them one by one. How about this pentagons one? You should begin, as always, by scribbling in the degree 2 vertices. So I go here, these ones, right? Because that's a degree 2, so I scribble those 2 edges. This is also a degree 2, so I scribble these 2 edges. Now, while you're doing this, you might as well, at the same time, disallow any more edges. Like this one here now has 2 edges already scribbled through it, which means that one is not allowed, right? Because if it were scribbled in, then you'd have 3. Okay, more degree 2s here and here. All right. What else can we do now? You got to look carefully here. There are moves that you can see here that you have to fill in. I'm looking at this vertex right here. I have disallowed one. So there's only 2 allowable edges that it could be, so it must be those 2 edges. So we must scribble in here and here. I hope that you saw that. Having scribbled those in, now we can disallow this one because I've already used 2 here and also here. This vertex already has 2, so we disallow that one. And that means now I can scribble this one in because now this only has 2 options. And this one here. Right? And then finally, what else? It's only right down here that we're looking at. Could it be that the Hamilton circuit uses this edge? No, it could not. That would make a smaller circuit here, so that one is disallowed. And for the same reason, this one we must disallow because that would make this smaller circuit. It looks big on the page, but I mean smaller in terms of the number of vertices it hits. It doesn't hit all the vertices. So this one also must be disallowed, and that means we have to use these 2. So there's the Hamilton circuit. Whoa, isn't that nice looking? I think that's nice looking. I hope that you wrote down some narration. I didn't just because I don't have enough room. For these last 2, I am going to narrate and write it down. All right, I hope you got that one. Let's try this one here. We begin with scribbling in the degree 2 vertices. So that would be, this one is degree 2, so I can scribble across here. This one is degree 2, so I can scribble across here. And then this one is degree 2, and this one is degree 2. And the corners of the diagram are degree 2, right? So this one, this one, this one, this one, and also on the other corner, this one, this one, this one, this one. All right, what can we do from there? I think actually we can immediately say there is no Hamilton circuit. All of these that I drew already have been forced on me, but you can see, like right here, this vertex now has 3 scribbled edges meeting it. So we draw in the degree 2 vertices, and this immediately means no Hamilton circuit, since 3 edges are meeting right there, right? So there's no Hamilton circuit because all I did was scribble in the ones for the degree 2s, but it already forced me to meet in this 3-way intersection, which is not allowed. All right, let's look at this one. I hope that's what you said for that one. All right, for this one, this is a bigger example. Let's, as always, begin by sketching in the degree 2's. All right, that would be here, also here, right? Here, I'm looking in the corners mostly. Here, this is a degree 2 there, and down there, right? Okay, is that it? I guess that's it. What else can we say now? Those are degree 2's. It might be a good idea to look next for any degree 3's, and if you get lucky, you can disallow something at a degree 3. For example, right here, this is a degree 3, but I see already 2 edges from the circuit are meeting that vertex, and so we can disallow that guy, all right? So this is because disallow since 2 edges already scribbled. Right there. All right. Can we do that same thing anywhere else? That would be nice. I'm not sure if we can. There are a few more edges that we can rule out because of the no smaller circuits rule. For example, this diagonal here is not allowed because I cannot make, that would make a smaller circuit right there. So X this out, and similarly that diagonal. So we also, I'm just going to say no smaller circuit. That's why I X'd that, and also, well, that one down there also. I don't want to make too big of a mess with all these arrows, but that one also. All right, so those are disallowed. Now, did that get us anywhere? Let's just look around this one. Is there any more deductions we can make just because we crossed that one out? Actually, we can right here. Since this vertex, it had degree 3, but I crossed one of them out, it must go through here, right? You got to have 2 edges that meet that vertex. That's the only one there. So this forces that edge right there, right? Anything else? What else? A similar thing happens right here, right? This one had degree 3, but I X'd out one of them, which means we must use that edge right there. So that forced that and also that. Okay. It seems to me this edge right here would make a smaller circuit, right? This one's kind of tricky. You got to sort of stare at this one for a while before you realize that. It's true though. This edge right here would make a smaller circuit, so I disallow that one also. Smaller circuit is how we disallow this guy here, right? Then, having disallowed that one, I believe the vertex at the top, in order to have 2 edges, we must scribble that, right? That forces this edge right here. Okay, are we making any progress? Probably. Now I have 2 edges going through here, so this one is not allowed because that hits that one already. What else can I say? What more can I say to you? I think maybe at this point we can just try to fill in the Hamilton circuit. Knowing that it must use this part and also this part and also this part, can we kind of fill in the blanks and make this actually work? Let's imagine if I scribbled in here. So I'm just going to say now guess. It would be nice if we didn't have to do that. Although, like I said, these 2 simple techniques, they do not always suffice to find a Hamilton circuit. Sometimes you're just going to have to break out the old guess and check. What do you think? I already have some guidance about what I have to use and what I don't have to use. I'm going to put all my guesses in another color just so that we can tell the difference between what I know for sure has to be and then what I'm just sort of making up. But it seems to me like you can actually make this work out. Let's see. If I scribble this one and then also this one, so I go, now I got to hit these 4, but you can do that, right? If I do this, that. That looks like a Hamilton circuit to me. All right? So this is my Hamilton circuit. It may be actually, if I just guessed that, maybe then I could have deduced all the rest of it must have gone in a certain way. But this is what you have to do sometimes. It looks like a big G, I guess, my Hamilton circuit. Excellent. All right, that's all we're going to say about finding Hamilton circuits. It's a hard problem. Those two tricks will sometimes let you figure it out, or at least give you a great start before you have to start guessing and checking. What I want to talk about for the rest of the time this time around and several times later on is a certain type of problem which is very important these days, especially in graph theory. I want to talk first about which it has to do with Hamilton circuits. I want to talk first about a special type of graph called a complete graph. Complete graphs. So a complete graph is one in which every two vertices have an edge between them. So this is an example of a complete graph. A complete graph is one in which every pair of vertices has an edge. That's called complete because it's like it has all the possible edges that there could be. There are those edges. Every pair of vertices has an edge. So this is a complete graph with 3 vertices. You could draw a complete graph with 4 vertices. It would look like 4 things, and then they are just connected. Every possible connection. So the lines are crossing here, but there's no vertex in the middle. This is a complete graph on 4 vertices. Actually, these have names. This one is called K3. This one is called K4. K stands for complete. Now, K actually is, I believe this comes from the mathematician Kuratowski, who was a 20th century mathematician who did a lot of graph theory work. The complete graphs. K5 looks like 5 points in a pentagon. And then they have all possible combinations between them, all possible connections, all possible edges. This is like Satan's favorite graph, K5. K6 is the last one I'll draw. You begin with a hexagon of points and then connect them in all possible ways. Make sure you get them all. Did I get them all? No, I need these. All right, that's a picture of K6. These are called complete graphs. Complete graphs are ones in which there is an edge between every vertex. All right. An interesting thing you can say about complete graphs. Let's talk about Hamilton circuits in complete graphs. I'm just going to draw. Let's draw K5. Let's talk about K5, the complete graph on 5 vertices, and I'm going to give names to the vertices. Let's say they go A, B, C, D, E like that. All right, and the edges, there are edges everywhere. Anywhere you want to go, you can go because there's an edge. All right, A, B, C, D, E. What are the Hamilton circuits? Are there Hamilton circuits? What are they? Are there Hamilton circuits? The answer is yes. Can you think of a Hamilton circuit here? Let's just write it down. Well, I think the easiest way, remember you have to make a circuit which visits every vertex. The easy way would just be go around the outside, right? You can go A, B, C, D, E, A, right? I'll write the circuit that way. A, B, C, D, E, A. That is a Hamilton circuit. Okay, is there another one? Are there other ways to do it? Well, you could go the other way around. All right, so that would be A, E, D, C, B, A. Okay, that's another one. Is there another way to do it? There are actually other ways to do it. For example, I will write another one. A, D, B, C, E, A. What does that look like on the picture? So I'll draw that one over here, just so I don't have to screw up that picture. A, D, B, C, E, A. Looks like A, D, B, C, E, A. Right? This meets, it visits every vertex, and it is a circuit. All right? Can you see another one? How about this one? I have another one. I'm thinking of another one. A, C, E, B, D, A. That's another one. This one looks like A, C, E, B, D, A. That's a cute little star, isn't it? Can you think of another Hamilton circuit in this graph? Actually, would you believe me if I said any way you write these letters down, will be a Hamilton circuit, right? Like, I'm just going to invent one. I'm not even looking at the picture. I'm just, how about A, E, B, C, D, A? I just wrote some ordering. That is going to be a Hamilton circuit. It starts and ends at A, so it's definitely a circuit. It hits every vertex, so it's a Hamilton circuit. The only thing really you should worry about is, like, do these edges actually exist in the graph? Like, I just, at random, I wrote E to B. Is there even an edge E to B? Well, since I'm talking about a complete graph, there is automatically an edge from every vertex to every other vertex. So can I just say any rearrangement of these letters? Well, if we begin and end with A, those have to be like they are. But then anything on the inside can be rearranged any of the way we like. So any rearrangement of, can I just say B, C, D, and E gives a Hamilton circuit. Right? Starting at A, right? And of course, if you wanted Hamilton circuits starting at a different point, then you would put that point on the two outsides, and then you would take all possible rearrangements of the other points. All right, any rearrangement. So you can say, are there Hamilton circuits? Yes, absolutely there are. In fact, you can say specifically how many Hamilton circuits there are, because any Hamilton circuit consists of some choice of a rearrangement of those 4 letters. In this example, there are 4 of them. In fact, we can say very specifically, we've talked about this before actually, in other contexts, instead of rearrangements, we call those permutations. A permutation is just a rearrangement. Anybody know, do you remember? We talked about this a long time ago with something about weighted voting. How many permutations are possible for 4 things, A, B, C, D, E? Or in this case, they were B, C, D, E, not A, B, C, D, E. 4 things, B, C, D, and E. How many ways are there to rearrange 4 things? The answer is 4 factorial. This is something we talked a while ago about. 4 factorial. So in this case, can I just say in Kn, if we are in Kn, the number of Hamilton circuits in Kn, if you just choose a starting point, the number of Hamilton circuits starting and ending at that point it's something factorial, right? It's the number of ways to rearrange all the other letters. If there's n letters total, one of them is A, all the others would be n minus 1. There's that many left over. And so what you get here is n minus 1 factorial. The number of Hamilton circuits which start and end at a particular place is n minus 1 factorial. If you want all possible Hamilton circuits, regardless of where they start, it would be just straight up n factorial, which is slightly greater. All right, but anyway, can I just say this is very large? All right, when the n is big, there's a lot of possible Hamilton circuits. I wrote down myself just a little chart here for your enjoyment. If the n is 3, then what is n minus 1 factorial? That would be 2 factorial, which is 2. So, okay, that's not very big. If n is 4, this would be 3 factorial, which is 3 times 2 times 1, that's 6. 5, this would be 4 factorial, which is 4 times 3 times 2 times 1, that's 24, which is getting to be a little bit more. And then if n was 6, this would be 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is quite a bit. It's 120. So, do you agree? This is very large. Even if the n is not really big, this number, n minus 1, is quite large. But that's just the way it works. What we're going to talk about for the next few times, I want to get started on it today, and then we'll talk in more detail next couple times, is a little something, a very important graph theory problem called the traveling salesman problem. The traveling salesman problem.